The greedy algorithm doesn't always produce the shortest word, not surprisingly. So basically, in a sense, sort of locally optimizing each step doesn't give you doesn't optimize globally. And in particular, for example, with the Černý construction that requires exactly n-1 squared, for this specific construction for each n, if you apply the greedy algorithm, you definitely end up with something larger than n-1 squared. Right? So the greedy algorithm has no hope of actually proving the full conjecture. And then also, another general challenge is that there's actually very few synchronizing automaton that actually comes even close to the Černý bound. Right? So it's definitely a tight bound because of this construction, but things that actually hit that bound are relatively rare. Actually, if it's synchronizing, most of the time it synchronizes very quickly. Right? So you can usually find a fairly short word that will synchronize it. And even, so the Černý construction is actually the only known infinite family that actually hits the bound of the n-1 squared. And outside of that, they have a handful of specific cases, I think, for like 3-state automaton. They have a few other examples that actually require n-1 squared, which would be 4. Right? They have a few of length 4. They have exactly one of length 5 that will actually hit this bound, and exactly one of length 6. And then that's actually all that's known that actually hits the bound. And everything else generally synchronizes much quicker than this n-1 squared. And yeah, even getting things that come close to the bound is difficult. And then in general, also finding the minimum reset word is kind of a computationally hard problem. So to even sort of brute force and look for specific other automaton is generally, you can't go very far. I think Trotman, the guy that improved the bound most recently, he did some computational work with it, and I think he verified that the conjecture is true for up to, I believe, 10 states if you have 2 letters, and I think up to 7 states if you have maybe like 3 or 4 letters. So, but even then, it's you can't get very far. And so also let me comment. I'll jump over here. So structurally, also you can interpret this a little bit differently. So if I were to kind of separate the A's and the B's, so I have sort of a 1, 2, 3. So for the map B, it's just a permutation. A, 2, 3. And so here I just separated the kind of the A and the B subgraphs. And even here, so intuitively. So having a permutation can never really help you synchronize. It just kind of shuffles around states. And so you always end up with at least one letter that is not a permutation, where it allows 2 states to kind of map down into 1 state. And so, intuitively, if you have, if you have more sort of vertices where things can kind of map together, that should help things to synchronize quicker. But even that, proving some sort of concrete result about that, as far as I know, is not really known either. The issue is, if you try to, maybe prove it by, shifting some things around and showing, if I move this edge over here, that now it's, going to synchronize slower. the problem is actually proving that they'll actually synchronize slower. Because what happens is if you tinker around anything here, then in the general automata, what was previously a reset word is now totally different. So finding the bound on that new reset word then is extremely difficult as far as I know. And so shift. And so now I had also mentioned that there are specific classes of automata where this was also shown to be true. So in particular, in 1998, Book showed that if one of the letters works as just a cyclic permutation, then the conjecture holds. So, for example, in the Černý's construction, this one functions as a cyclic permutation. But in general, if in here there's no restriction on the number of letters either. So just any synchronizing automata, if it has one of the letters is just an n cycle basically, that the conjecture will actually hold. Let's see. Also, in 2003, Kari showed that if the underlying directed graph for the automata is Eulerian, then the minimum reset word will be no more than the n-2 times n-1 plus 1, which is below the Černý bound. And so for the so if the underlying directed graph is Eulerian, then it also satisfies the Černý bound too. And so and I believe for this, as far as I know, it's not even known if this bound is tight either. So it's possible that this bound could also even be further lowered in the Eulerian case. And also, the letters themselves, you can basically view them as maps, right, from state Q to itself. And you can imagine the letters as generating a semigroup. And so with that sort of perspective, there's also been some work done where, if this, based off the letters you have, the semigroup it generates, if it has maybe some specific properties, then the conjecture is also true. But that's also had, I think, very, very little concrete things have been done there too. And so, let's see. Should I mention anything else? And lastly, I guess even with the Eulerian case, in a certain sense.
So it's not known whether it's tight.
Yeah, it's not known, as far as I know. It's not known.
But for small n, it's known.
I don't think anyone's really looked at it too closely. And I think, in the paper that it was published in, the author had mentioned that, he was maybe a little surprised that the bound was actually a bit lower than what was needed. I think in hindsight, I think the Eulerian case, I guess, it's a fairly balanced directed graph. And so you would think that that would make things harder to synchronize. But if you think about what this Eulerian case forces you to have, basically, if the underlying directed graph is Eulerian, then so basically you would have to have either multiple things that are not permutations to balance the n degrees for each of the vertices. Because anytime you have something like this, the vertex 2 has, state 2 has n degree of 2, state 1 has n degree of 0. And so you need another non-permutation that would help balance the total n degree. And so in the Eulerian case, in a sense, you'd have multiple maps like this that are not permutations, right? And so you would expect that to help out with synchronization. Like you have more options where states can kind of map down. And so, yeah, so it's not been shown whether it's tight, but in a sense, it's not, I guess, in hindsight, it's not too surprising that it's actually below the specific Černý bound too, because you're forced to have multiple things of this nature. So, I think so. Otherwise, I think I'll wrap up here.
Thank you very much. Do we have time for questions? So, so this is any been attempts to make the greedy not so greedy, and see if you go twice, jumping, reducing the finite 2 at a time, to make it a little bit better than.
Or k at a time.
Yeah, not as far as I know. At least not anything I saw that was actually published. The problem is, well, I guess the challenge is that to get the bounds that they have now, sort of the I+1 choose 2 bounds. Basically, there's no real good natural way to extend it to further along, as far as I can tell. So yeah, as far as I know, they haven't attempted to. I mean, even the whole kind of being able to sort of kind of go halfway quickly, you know, was 28 years after the original bound was set. So yeah, not as far as I know. I do think in general, the bound, if I jump way back. In general, this bound here, in a sense, it gets worse and worse as you shift along. So I guess any hopes of maybe improving this bound would be to maybe improve the bound somewhere sort of on the far side. But you know, I guess one more challenge too is, so this bound is basically derived by saying, you know, maybe, you know, at this point I have 2 states left. Then, you know, I need to find somewhere that'll map these 2 states down to 1 state. And, you know, and then so what's the worst case? How many states can I possibly have in between, you know, till that happens? And so I believe it's actually possible. It's possible to find a pair of states. I think in the Černý example, it's possible to find 2 states where if you start at those 2 states, then it takes forever. It almost reaches that upper bound to actually synchronize. Now in practice, what happens is as you're synchronizing this thing, you won't hit that sort of worst case 2 states as a starting point there to kind of finish. But yeah, as far as I know though, yeah, there's been no further improvement based off of this greedy algorithm. So.
Is there anything less than a reset state?
What's that?
Well, that's what you said, partial, it works for parts, then go down to 1, we go down to 2 or 3. Something less than a complete reset word.
Yeah, actually, you mean if it is synchronizing, or you mean just for a different?
No,
synchronizing means there's a reset word.
Then as a notion.
Maybe the notion, relax the notion somewhat. Like, okay, it's not a reset word, but it's, yeah.
Yeah, but
it's almost a reset
there's a
word.
more general conjecture that Brian mentioned. There was a more general one. If you go k steps down, it's k squared. But this has been refuted.
Yes.
No, nobody knows exactly. There may be some more general, more weaker conjecture.
Yeah, so before there was a conjecture that for each k, you can do this. So before there was this conjecture that for each k, you know, so as a generalization of the Černý, because in the Černý case, if k is n-1, then it's exactly the Černý conjecture.
That's a very good question.
It's a natural.
But yeah, so this has been shown to be false. So the 6-state one that hits the n-1 squared breaks after the halfway point. And you actually need more than the k squared.
But it's possible that a slightly weaker version would be true, right?
Yeah, maybe if you were to kind of add this a little more here. Yeah. Now there's also an additional improved variation of this conjecture where, you know, so an automaton, for it to be synchronizing is a very specific property, you know, that you can map all the states down to 1 state with some word. So that, you know, you may have automata where that's not the case. You know, maybe the best you can do is you can map down everything to 2 states. And so there's a version of the conjecture where this would be true if It basically was if you can reduce it down k, if k is as far as you can reduce it down to, in a sense. So what's the so basically, if the best you can do is go down to 2 states,
And then you get stuck.
then there's a reset word of n minus 2 squared, or it's not a reset word, but there's some word of at most n minus 2 squared that'll get you there.
And it had not yet been computed.
No. Yeah, so this revised conjecture has not been, as far as I know, people haven't really looked at it too much either, as far as I know. Actually, it actually required a lot of digging around to even find it. So.
Thanks again.